This is the Module 3 Advanced Concept presentation on the oxygen binding mechanisms to heme or hemoglobin. Our objectives here explain how oxygen binds to heme if any structural changes occur, explain the difference between binding capacity of oxygen to heme in the lungs versus binding capacity of oxygen to heme in the capillaries, and finally explain how carbon dioxide interacting with water can affect the pH of capillaries. So to begin, we have the hemoglobin structure, which we can see on the bottom left here, taken from the textbook. It has a few distinct structures right off the bat to it, which we'll go into. The picture on the top left is the molecular breakdown of the heme molecule, which are these green structures you can kind of see embedded in the helices, the red and blue helices of it, but we'll go into that. It's probably most notably defined by a quaternary structure, meaning multiple polypeptide chains supported by non-covalent forces, primarily weak forces, a la van der Waals interactions. And those polypeptide chains are the coils, the helices you see in the bottom left picture in blue and red. So a complicated protein structure that delivers oxygen throughout the body. Big difference between hemoglobin and myoglobin, which they're both part of the globin family and they both transmit oxygen. Is hemoglobin is found everywhere in the body, most famously in the bloodstream, and myoglobin is found only in the muscles of the body. It's a heterotetramer made up of the 4 distinct polypeptide subunits, the globins, and that will be kind of a recurring theme for the rest of this little presentation, sort of a rule of 4. So what makes that different from a homotetramer is that instead of 4 identical groups of these helices, you have 4 distinct polypeptide subunits, 2 alpha, which would be the 2 red ones here, and 2 beta, which would be the blue helices there. The heme group, which is the other major structure in this molecule, is a non-protein molecule. It's these green structures, like I said, and those green structures are made up of porphyrins, which probably most importantly have a central iron ion within them, which is the actual binding site of the O2 molecule. And it's the site of big importance, reversible oxygen binding, so that this hemoglobin can receive oxygen and then deposit it wherever it needs to go in the tissues or the capillaries of the body. It's a heterocyclic ring, which is the primary component that gives blood its red pigment, more purple when it's deoxygenated, more red when it's oxygenated, primarily in the arteries versus the veins. And these, porphyrin groups are further composed of pyrrole groups, which again harkens back to that informal rule of 4 I was talking about. There's 4 of those. They're heterocyclic ring structures containing 4 carbon atoms and 1 nitrogen atom. And those nitrogen atoms are the actual points that anchor that iron ion in place. So C4H5N would be the simplest pyrrole group. And like I said, those 4 nitrogen atoms kind of hold that central iron ion in place, which is going to be doing the work for us. So those 4 binding sites for oxygen in 1 hemoglobin, the 4 ions and the 4 porphyrins, which have themselves the 4 pyrroles. Oxygenation itself is the binding of molecular oxygen, O2, to a heme group. In an oxygenated environment, oxygen binds to the central iron ion, which results in an oxygenated heme complex, which would be the structure on the bottom right of the infographic from the textbook. And it's tough to see with your eye, but we'll get into the structures are slightly different on the right. So deoxyhemoglobin is when the heme groups are structurally non-planar, obviously lacking the oxygen. The iron atom of the heme group is pulled towards the histidine residue, which is the amino acid that's kind of tugging the iron in one direction of this hemoglobin molecule. So oxygen binds to hemoglobin to create oxyhemoglobin. And these are sort of the effects that we'll go into: alpha 1 and beta 1 polypeptides. And conversely, the alpha 2 and beta 2 contacts shift. This is a structural change. The quaternary structure changes. The alpha and beta dimer rotates around 15 degrees. The beta units close some distance between each other. And this cavity in the center that kind of shrinks a little bit from top to bottom is a solvent-filled central canal or channel that narrows, indicating the structure change. A crystal lattice of the deoxyhemoglobin, which kind of gives the hemoglobin structure, shatters under these forces when it's exposed to O2, and that iron ion in the center is sort of pulled in the opposite direction of the histidine residue in the porphyrin structure to become more planar, and this is known as a conformational change. And this increases the likelihood of O2 to bind to other heme groups in the structure. And at the bottom we see R state conformation, which is the oxygenated structure, and T state conformation, which is the deoxygenated structure. So the difference between binding capacity of the oxygenated to heme in the lungs versus the binding capacity of oxygen to heme in the capillaries follows on the graph on the left what's known as a sigmoidal or S-curve binding system. This illustrates a cooperative interaction between the binding sites. Binding of one ligand to one site affects the binding of another ligand to other sites, meaning more oxygen attaching means more oxygen attaching. So the binding of one subunit increases O2 affinity of the remaining subunits, the remaining three. And at a low partial O2 pressure, hemoglobin subunits independently compete for O2. They still combine, so there is a big increase in the slope despite a lower relative partial pressure because of this effect. And they plateau at higher pressure because they become saturated. All four have made bonds. The lung environment has a high partial pressure of oxygen. Intuitively, is where the oxygen enters the body first and foremost, where the hemoglobin becomes around 98% saturated. And within the capillaries, the partial pressure is lower, around 40 millimeters of mercury, where the hemoglobin becomes around 32% saturated with oxygen. This is sort of indicated by what's known as the Hill equation, which informs the degree of saturation of the ligand, the bonding of the oxygen to the ion, in the porphyrin group, or in the heme group rather, and the binding with multiple binding sites as a function of ligand concentration. So the more oxygen in the environment, the higher the partial pressure, the more the oxygen binds to the heme group, and then the more the structure changes, which allows for more oxygen to bind to it. And so, like I said, in other words, to say that the O2 binding status of a heme group is mechanically transmitted. So as it binds with oxygen, it sort of undergoes that state change from R to T, which corresponds with a structural change in the actual hemoglobin molecule, which makes its affinity higher to oxygen in its environment. And lastly, we have CO2 interacting with water. How can it affect the pH of capillaries? So this is known as an allosteric effector, meaning it's an outside effector of how oxygen is binding to hemoglobin. Carbon dioxide is one of those. Temperature is another. Environmental pH is the most relative one here. And it's sort of informed by what's known as the Bohr effect, which means a decrease in O2 binding affinity of hemoglobin in response to a decrease in pH, so a more acidic environment. So the lung pH is about 7.4. Tissue pH, the capillaries, is 7.2. Blood pH is 7.6. So CO2 needs to make its way back to the lungs from the tissues. So it's produced by respiring tissues. It reacts with water in the capillaries to produce bicarbonate, which is a base, and hydrogen ions, which is an acid. And you can see the equation below that sort of informs that. Hydrogen ions slightly decrease the capillary pH, while bicarbonate buffers it from dropping severely. And oxygen disassociates from hemoglobin in a proton-rich or hydrogen ion-rich environment and supplies the tissue, so it's deposited in the capillaries. This is part and parcel of the cooperative binding effect. So because it works in one direction, it works in the other. So hemoglobin with fewer bonded O2 decreases its future affinity to bond with O2 as hemoglobin transitions from that R state, the oxygenated state, to the deoxygenated T state. And so O2 is deposited into the blood or areas of the body, sort of where CO2 concentrations are the highest. So, in a sense, it supplies oxygen to the parts of the body that sort of need it the most, where the CO2 concentrations are the highest, where the acidity is the highest. Thank you, and have a good night.